So lesson 13 here. Yesterday we talked about network solids really quickly. We talked about how network solids, there's only really two things I want you to know. They are covalently bonded atoms, of course, and I underlined this stuff for you yesterday in the notes. Covalently bonded in a variety of patterns, and different, same element but have different network solids which consist of the same element that have different physical properties are called allotropes. Was the only other thing I asked you guys to know from that about network solids. Okay, and of course the examples of network solids are things like carbon. Okay, so carbon comes in graphite form, pencils, and diamonds kind of thing. Okay, so that was yesterday for that. Intramolecular bonding, don't forget, is what holds one molecule together. So for example, it's what makes sugar, one molecule of sugar. That's what holds that. It's basically covalent bonding. Okay, intramolecular bonding. Intermolecular bonding is things that are responsible for states, really, gases, liquids, and solids. How well this molecule holds to a different molecule, to a different one, to a different one, et cetera, et cetera. So there's three different types of forces that we talked about. Intermolecular, first one was dipole-dipole. And dipole-dipole, of course, remember, is just the positive end of one molecule to a negative end of a different one. Don't forget, dipole-dipole are polar. Okay? So they're polar molecules, of course. And like I said, difference in electronegativity. The negative end of one attracts the positive end of another one. The example we gave you yesterday was HCl. What I've drawn up there so far is intramolecular bonding, covalent bonding, sharing electrons not equally, mind you, partial negative, partial positive, yes? Okay? And I'm not gonna get carried away today. Okay? We got another HCl there. That's intra. Intermolecular bonding is right there, between molecules, what holds them together. Okay? In this particular case, since we got two polar molecules here, this is called dipole-dipole, dip-dip. Yes? Okay? The only difference between this one and the next one I'm going to draw, I'm going to jump to hydrogen bonding. Okay? Hydrogen bonding is the next one in your category there, HF. But I'm just going to draw it here just to show you the difference between these two and what's similar and what's different, basically. Don't forget, this is partial negative, partial positive, partial positive, partial negative. Yes? Exactly the same. Huh. Imagine that. There's an attraction between these two. Huh. Imagine that. They're both the same. This one's called hydrogen bonding because H is bonded directly to NO or F. That's important. Listen carefully. Going to give you some homework today. H, in order to have hydrogen bonding, you need to have H directly bonded to NO or F. Okay? They have to be together, bonded together. Otherwise, it's not hydrogen bonding. Okay? So, this particular case is. You might say those look exactly the same. Yes, because they're both technically dipole-dipole polar molecules. However, because, remember, this one is so much more electronegative than this one here, electron spends most of its time around fluorine. And because of that, fluorine has a partial negative and a very negative end to this molecule. Okay? Very negative end to that side of the molecule. Lone pairs enhance the negativity we talked about yesterday. Okay? What's left over on this side here, the hydrogen? Well, it's the partial positive, of course. You have that. Oops. Partial positive, you have that. Plus, don't forget, what's left around hydrogen? A bare positive nucleus, because that electron's spending more time around fluorine. So you very much have, if you want to think of it this way, right? Bare positive nucleus, partial positive. You got a very positive end. Okay? You have a very negative end on this particular molecule. Well, guess what? The other HF looks the same. Bare positive nucleus, partial positive. So you get a very positive end and you get a very negative end. Okay? Yes? Partial negative, lone pairs enhance the negativity, the attractiveness of that. So you get very positive end attracted to very negative end. It's not ionic. Okay? It's still very positive end, very negative end, but it's not plus minus. Okay? That's ionic. Okay? So don't get confused here with my little drawing up here of pluses and minuses. All right? Just, I'm trying to say that this is very positive, very negative. Very positive, very negative. It's a stronger type of dipole-dipole force. So strong it needs its name, hydrogen bonding. It needs its own category. How strong is hydrogen bonding? I'll show it to you. In some cases, it's 100 degrees Celsius stronger. Think about 100 degrees Celsius. That's a lot. Yes? That's how much stronger it is in some cases. In some cases. All right? So does it need its own category? Absolutely. Okay? So that's hydrogen bonding. The top one's dipole-dipole. Okay? Then we went to, there's your hydrogen bonding stuff there. You can read through all that. The example we gave you. And then we got to London. Okay? And London forces are for nonpolar molecules. Not solely for nonpolar, though, because remember, yesterday we talked about London forces. We talked about electrons go round and round, right? Well, guess what? Polar molecules have electrons that go round and round, yes? So polar molecules also have London forces, yes? All molecules have London forces. However, in nonpolar molecules, the only forces present is London forces, okay? So, we skipped through all this. If you want to describe London forces, it's basically in this paragraph right here, nonpolar molecules, blah, blah, blah. The example I gave you yesterday was hydrogen, okay? Hydrogen is nice and easy because it's nice and small. You got two electrons that go around hydrogen. When they're here and they're here, well, that's fine. They're sharing equally, blah, 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 all that other stuff. But they go around and around in an orbit. And at some point in time, you're going to get a slight distortion. So you might end up with one here, and you might end up with one, let's say, right here. Okay? So at this particular time, for this fraction of a millisecond of a second, you get this kind of charge on them. It's a temporary dipole, and that induces or brings another HH close enough to it to have a partial negative and a partial positive, and so on and so on. And this right here is London forces. Okay? Happens for a brief instant of time. Okay? But remember, you don't have three, you've got a cajillion of them. So if you had a cajillion attractive forces, that can be significant enough to give you, you know, to have an effect on that overall structure kind of thing, or on that overall molecule. It might be strong enough to change it from a gas to a liquid, or from a liquid to a solid in some cases. Okay, and we're going to talk a little bit about that today, a little bit, tomorrow mostly. Okay, but that's London forces. And remember, they don't stay on. They're not partial negative, partial positive. Guess what? Now it's gone back to this one here again, where everything is nice and neutral. And then the electrons keep going around and around. At some point in time, guess what? This one now is the negative one, and this one's the positive one, due to electrons going around and around. And this one would be the positive one, and this one would be the negative, and so on and so on. And then after a period of time, and it doesn't have to be this one all the time. You might say, is this the one that affects all of them? No, it could be any one in that. If you think about oxygen in the air here, oxygen is nonpolar, right? Look. Nonpolar, yes? Think about all the oxygen in this room. I can hear you metabolizing carbon dioxide. Sheldon says that on Big Bang. Think about all the oxygen in this room, okay? Oh, look, that one is not balanced right now. Partial negative, partial positive, partial, oh, but now it is. So they all turned off. And then I look over here. Oh, look, that one over there is partial positive, partial negative. And then next thing you know, all those kind of line up together. Okay? So it's not one. It's just they draw in other ones that are like themselves closer to each other. Right? And remember, we're drawing two-dimensional stuff. You might have one here. You might have one here. If they match up, good enough. This one might not, but this one does. Hey, look, I like you. Oh, I don't like you. It's kind of like grade 11, dating. I like you. No, I don't. Yeah, I do. No, I don't. I don't know. I have no idea what grade 11. I never dated. How would I know? It's true. So, and once again, it kind of induces the next one, brings it closer, helps form it to that. So there's a picture of, you know, a balloon to a wall, for example. It induces, it brings the negative charges out towards it, so it's attracted to each other, et cetera, et cetera. And then I think we got to about here yesterday, yeah? Roughly? So, obviously, guys, London forces are quite weak, yes? They're temporary. They don't last very long. Depends on, you know, electron goes around pretty darn fast. So they're on, they're off, they're on, they're off. They're temporary. They don't last very long. But you get a lot of them, and they can have a significant effect, all right? There is two main things that affect London forces. And those two factors you need to know absolutely. The first one, I don't know, did we get this far yesterday or no? I think we did, actually. We talk about the size, okay? When we talk about the size, and it tells you all this stuff here, here's what I really want you to know. It is the number of electrons. Okay? And yesterday, I, in fact, even gave you an example, I think. I said, you know, think about hydrogen. Hydrogen's got how many electrons going around and around? And the answer was 2. Yeah? What's the chance of distortion there? Well, it's okay. Definitely okay. There's a chance. Yeah. Then we look at something like iodine, for example. Iodine is I2. I have no brighter, clever friends, yes? Et cetera, people stupid. So II, 53 and 53, if we look up all the electrons. Because remember, once again, don't get confused. And don't get confused when you draw these. When we draw them, we're talking about valence electrons, right? How are they going to become more stable? When we think about London forces, we need to think about all the electrons that are moving. How many electrons are moving? 53 and 53, 106 altogether. Yes? Do you think 106 are going to be completely balanced at every possible, exactly balanced at every possible second? Well, geez, that's a lot of electrons to have exactly 53 and 53, yeah? Probably not going to happen, right? In fact, probably very rarely will it happen. So in fact, you're probably going to get, therefore, if it's unbalanced, you're going to get a lot of London forces, a lot of partial negatives, a lot of partial positives. You're going to get a lot of that unbalance. A lot of that unbalance equals a lot of London force. A lot of London force equals stronger, okay? So between these two, I2 would be a stronger compound, or molecular element, I guess you could say. I can prove it to you right now. If it's strong, intermolecular force is what we're talking about. When we talk about intermolecular forces, we are talking what holds this molecule to this one, yes? HH to HH. Look, what's hydrogen? It's a gas, right? So how much attraction is there between HH and HH? Not a lot. Look at I. Right? Lots of attraction. It's a solid, right? Because it's got so many electrons going around and around that, okay, there's so many of those partial attractions that, in fact, it's pretty good at attracting each other, II to II to II to II. It's so good that it's actually in solid form, okay? So size is a factor of London forces. The more electrons you have, the better chance of distortion. The better chance of distortion, the more London forces you have. The more London forces you have, the stronger it is. And that goes for all molecules. Yes? All of them. Because London forces is in every molecule. The next thing we're going to talk about is the shape. And the shape, turns out, linear is better. Okay? It rhymes almost. The part does. Okay? Here's AX4. It's kind of spherical. You might say, no, it's not. Well, it kind of is. Okay? How close are you going to be able to get another AX4 to that one? Yeah, not great. Okay? When we talk about AX4, we talk about we talk about how much contact area is there between those two molecules in the big scheme of things, right? And the answer is not a lot. If you think about spherical molecules, they can touch basically in one spot for the most part. Now you might say, well, I could get these two a little closer together. Well, you probably could, okay? But generally speaking, we consider AX4 to be kind of somewhat robust, roundish, okay? Then you think about things like AX2, and a common AX2 one is like carbon dioxide, for example. How close can these two molecules get together? A lot closer, okay? Because they're both kind of flattish. So one can sit on top of the other one pretty well. Yes, could they end up like this? Absolutely they could. But they could also end up like this, okay? Could this one ever get on like flat like that? No. It's going to be like this, and no matter where you go around, it's going to be one point only, okay? Linear turns out to be better. Because remember, if there's distortion, it induces the one beside it. It brings that next one closer to it. How close can this one affect this one? Much easier, because there's more contact area right there, more surface area to contact each other with. So whatever happens on the bottom one affects the top one, and so on and so on, okay? This one has very little contact here, okay? Very little contact, so how well can AX4 affect another AX4? Will it? Absolutely it will. How well? Well, as close as they can get together, which is not very close. So we would say spherical usually is, worse, I guess you could say. Now, I'm not saying that they don't. That's absolutely not what I'm saying. I didn't say they don't. I'm just saying it's not as easy for it to attract or affect the next molecule to it. Okay? I can prove it to you. Here. Eventually, this is what you guys will do at some point in time. Okay? And this one's pretty straightforward, actually, for the most part. We eventually will talk about boiling points and melting points. Boiling points and melting points, if you think about it, are what changes solid to a liquid to a gas, yes? Boiling point, melting point. Solid to liquid, melting point. Liquid to gas, boiling point, yes? Solids, liquids, or gases depend on intermolecular formula or intermolecular bonding, yes? How well they stay together. So think about all that stuff. When you heat up something, you are breaking intermolecular bonds, yes? When you melt sugar, you are changing solids to liquids. Solids are locked in, liquids have a little bit more motion, and then eventually gases, where they're kind of free of each other. There's still some attractions, but not as many, okay? So, here we go. This is eventually what I will ask you to do at some point in time. It probably won't be these two molecules, but nonetheless. Look here. This is what we call pentane, C5H12, and in fact, that's something that's part of organic chemistry. You'll name that next year in Unit 3. This is called C5H12 here, okay? C5H12. That's called pentane. This one over here, by the way, is called neopentane. We wouldn't call that in organic chemistry next year. That's kind of its, its name that they would call it. We would call this something different. We would call this, let's see here, dimethyl propane is what we would call that next year. But having said that, they have the exact same formula, yes? This one's also C5H12. That's why we picked it, by the way. Okay? C5H12. So, All right, well, you know, when we talk about, by the way, one more thing. I'm going to tell you right now, this is important for your homework. When you get long chains like this of carbons, we consider these to be non-polar. Okay, and I'm going to get you to draw some today so you'll actually see. Does it look like everything cancels each other out? And the answer is yes, it does. Okay. Does this look like it cancels everything out? This is also considered to be also non-polar. Okay, symmetrical all the way around if you want to think of it that way. Sure it is. C in the middle, C to C, C to C, C to C, and then you got H's, H's, H's. Everything cancels each other out. Very symmetrical. Okay, these are both non-polar. These are both London forces. Let's talk about size. London force based on two things, size and shape. So let's talk about size. How many electrons do you have? This is something we need to do here and be able to do. How many electrons do you have in C5H12? And remember, we are not just talking valence electrons here, because they all move. Yes? So shape, if we're doing, you know, how do you connect C5H12 together? Yeah, we do valence electrons. But are all the electrons in carbon moving? Or all the electrons in hydrogen moving? Yes. We need to count all of them then. C5H12, carbon's what, 6? So 6 electrons, 6 protons, 6 electrons, that's 30. That's 12. We got 42. Obviously, in this case here, guys, we also have 42 electrons. It's the same formula for crying out loud, yes? So obviously, they'll have the same number of electrons. What's different about these two? It's the shape, yes? Look, spherical, kind of AX4, little bit of contact, right? More linear-ish, you might say ovalish, sure, but more linear-ish, more contact right here. True? Okay. So which one sticks together better out of these two? Which one has stronger London forces? It would obviously be that one. Yes? Okay. Now, look at both of these for a second here. Look at their boiling points here. Okay? And I want you to go with me on a journey. We're going to go outside. Not really. And we're going to take the oven out there with us with 2 pots. Right out there. It's 0 degrees Celsius. It's winter. Snow freshly fallen on the ground. You guys don't like snow? All right. So we're outside. It's 0 degrees Celsius. At 0 degrees Celsius, this is a liquid. And so is this, because this is their boiling point, which means they turn to gases, yes? So we're outside at 0 degrees Celsius, nice fresh snow. Look over the mountains, fresh snow. Skiing, all that stuff. It's 0 degrees. We put both of these in the pot, and we turn both burners on at the same time, okay? 0 degrees. So we get to 5 degrees Celsius, we get to 7, we get to 8, we get to 9.5, and guess what happens? This one starts to boil. And that one starts to boil. What does that mean? The liquid, all those intermolecular forces that have connected all of those neopentanes, if you want to call them that, are starting to break, okay? Enough energy has been given to break that intermolecular force, that London force in neopentane, and they start to break apart from each other. They start to break those intermolecular forces or those London forces, and they're starting, and you break enough of them that they're turning into a gas now, so that they're kind of free of each other. Okay, they're still attractions, but they're farther apart from each other now. So this one breaks apart first. Why? Because that's the only contact we have between molecules. Okay, not very much. It's a weaker London force. They boil first. Okay, we have to go to 10, 20, 25, 27. We get to 30. We get to 32. We get to 36.1 finally. And only then do we have enough energy. Those are so well stuck together. These ones right here, they're so stuck together because of their linear shape that it takes another 27-ish degrees Celsius before we can start to break those bonds between the linear ones. Okay? So finally at 36, they start to break apart now, okay, and turn into a gas. So between these two, linear is the better shape, all things, other things being equal, okay? They have more surface area, they have more contact with another molecule, they're just simply stuck together better. That almost rhymes and sounds like a song, okay? They just stick together better, all right? Because they're linear, there's more surface area. And that proves it right there with the boiling points, 36.1 and 9.5. Okay? Much stronger. All right? Everything else is exactly the same. Same C5, same 5 carbons, same 12 hydrogens. Everything else is all good. Okay? So, that's what you need to know from that there. So network solids, like I said, those two things. Dipole-dipole, hydrogen bonding, and London forces. I'm going to get you guys to do a little bit of work here. So I'm going to get you guys to copy down these compounds today. And I want you to draw them quickly. And then I want you to tell me what kind of forces are involved. Intermolecular forces, for example. Okay? So I want you to draw these and name the intermolecular forces. I'm going to throw a couple tricky ones in here. So I just want you to, once again, draw them. I do want you to draw them. You don't have to tell me the formula or the name of that formula or the shape or the bond angle or whether they're polar or nonpolar. However, you do have to use polar or nonpolar to tell me what kind of force is involved. Okay? So, here we go. pH3. CH4, pH2F, NH3, H2S, NAF. Let's see here. So draw and name the intermolecular force. 7 is CHCl3. I'll get out of your way right away. NH2F. C2HF. 10. C4H10. C4H9F. And let's do 12. CO2. Okay. So listen, stop for a second. Look at me. Here's what you're going to do. Listen. Okay? Stop. Look at me. You're going to draw them out. Okay? Decide whether it's polar or nonpolar. If it's nonpolar, guess what? It's what kind of force? London, right? Done. If it's polar, you have to decide if it's hydrogen bonding or dipole-dipole. It'll be hydrogen bonding if there's an H bonded directly to N or F, it's hydrogen bonding. Otherwise, it's dipole-dipole. Okay? Yes. Okay, go. All right, so drawing these. Okay, here we go, guys. pH3. We're actually going to have a little quiz on this tomorrow, by the way. pH3, AX3E. Okay, obviously, trigonal pyramidal. We're going to go over that quiz right away here. Trigonal pyramidal, 107.3, blah, blah, blah. Okay, polar. So then you have two options, dipole-dipole or hydrogen bonding. You will pick dipole-dipole, yes? Okay, because there is no H bonded to N or F, therefore it's not hydrogen bonding. Okay, CH4. That's AX4 tetrahedral, blah, blah, blah. This is nonpolar, and therefore, as a result, only London forces are present. Okay? Nonpolar London forces. Don't forget, there is London forces in pH3. However, In the big scheme of things, which one's probably more prevalent, which force is more prevalent, which one's stronger usually? Dipole-dipole. So that's what we listed as that. Does it have London forces? Yes. But we usually call it dipole-dipole first because that's what the major force is involved there. Okay? pH2F. Okay, you guys need to quit talking. I'm not sure why you are. AX3E, polar. Okay, so dipole-dipole or hydrogen bonding. This is dipole-dipole. That's why you draw them. Okay? Don't assume, just because H and F are in the formula, don't assume it's hydrogen bonding. Is H directly bonded to NO or F? No, it's not hydrogen bonding then. You need to have H directly bonded to those because, remember, highly electronegative atom, bare positive nucleus, yada yada. There is no bond between H and F here for that to happen, right? There is not, remember how it starts, H has to be bonded to N or F. Well, it's not bonded to F here, okay? So this is dipole-dipole. That's why we're doing this. Okay? Polar hydrogen bonding, yes? In fact, you got numerous H bonded to N's there in this case. But of course, we're looking at this combined to another one would involve hydrogen bonding. Okay? H2S would look something like this. This is dip-dip. Dipole, polar, AX2E2, tetrahedral bend, 104.5. Okay? NAF, I just threw that in there just to see. That's, well, let's see, that's ionic. Yes? Does that have partial negative, partial positives? No. That's got a full positive, full negative, yes? Okay? So we're going to call that one, that's just ionic. Okay? When we talk about the partial positive, partial negative, remember we're focused on molecular stuff. How do you get partial stuff? Remember, the electronegative atom's not strong enough to fully pull that over and say, I'm just taking it positive, negative. It's going to share, not equally, but or sharing equally, whatever, but this is ionic. Okay? CH3Cl. There's 8 there, trust me. If you can't see them, they're there. The Carter machine gun approach. CHCl3, okay, this one is polar, so therefore dipole-dipole. Or hydrogen bonding, but in this case, of course, dipole-dipole. Okay? NH2F. And once again, it honestly does not matter where you put the F. Okay, usually I like to keep it symmetrical and put the H's in the F, but I thought I'd switch it up. It doesn't really matter. Because remember, this ultimately is three-dimensional anyway. So when you look at it three-dimensionally, well, big deal. This is most certainly polar, first of all, because it's AX3E. Okay, and it most certainly is hydrogen bonding in this case, because you actually have H bonded to N or F here. So this is hydrogen bonding. Okay. H is directly bonded to N or F. It could be 1, there could be 2, there could be 3, okay? So it doesn't matter how many, as long as somewhere in that molecule, that huge ginormous one perhaps in some cases, as long as there's an H bonded to an N or F, it's hydrogen bonding, okay? It doesn't matter where, doesn't matter how many, just somewhere, okay? C2HF. I gave you this one because ultimately, guys, you know, we probably, we haven't drawn maybe some of these yet, and that's fine, but we should be able to. C2H F. C's probably have to go in the middle because they form the most bonds. H is only able to form one bond, yeah? So we should probably put it over here, like so, right? Maybe one. And F can only form one bond, so I'm going to put that one over here. Now, you may say, I don't want to put it there, I want to put it over here. Well, that's fine. You can do whatever you want. I don't really care. The question becomes, Do you actually have 8 around each one where you need to? Does hydrogen have 2? Because if that's not the case, then you can't draw it. It's that simple, okay? This can hook up, these two can hook up, those two can hook up, and you'll end up with something like this here. Yes? And honestly, I think that's the only diagram you can have for this one. I don't think anything else is going to match up for you, okay, as far as that 8 around it. In some cases, yes, there's more options. I don't think there is in this one. If there is, and you get 8 around each one and you're happy with it, that's fine. I don't care. But like I said, not always. Just, yeah, whatever. Fine, yeah. Sure. As long as you have 8 around each one, okay, that's the main thing. So I don't care what it looks like, but that's the deal there. You know, once again, this doesn't work out to be AX2 or AX3 or AX4, AX3E. But if you look at this, hopefully we understand that this one's polar. Does it look like everything cancels out? Probably not. Okay, it's not very symmetrical. So this would be dipole-dipole. Okay, in that particular case there. Then we get to C4H10. C4H10, when you get something like this, guys, I'm going to tell you right now, it's probably going to look something like this. Okay? C4H10, butane. Okay? Butane, C4H10, these types of molecules tend to be non-polar, right? Everything kind of cancels each other out. Kind of somewhat, if you want to think of it this way, somewhat linear-ish, okay? Maybe more spherical, but if you look at the big scheme of things, I showed you C5H12 earlier. This is C4H10. But somewhat linear-ish, okay? Non-polar, this would be an example of London, okay? But whenever you get these long carbon chains like this, and this is important to know, we would consider them non-polar. Does everything cancel out? Yeah, it probably does. Okay, it's very symmetrical. You can see it's the same thing all the way around. Does the carbon-to-carbon bond cancel each other out? Does the carbon-to-hydrogen cancel out? Yeah, usually it does. Okay, so those long chains like that we consider to be non-polar. The next one was C, and I gave that one to you right after this one for a reason. C4H9F. Yes. So I don't care where you put the F wherever you want. I don't care. You know, once again, almost identical. But now, is everything the same all the way around? No, it's not. Are we going to have a polar end to this molecule? Absolutely. Probably the negative end over here. Probably the positive end kind of over here-ish more, right? So we would say that this is most certainly polar, and in this case, dipole-dipole. Even though, you know, we have a bunch of H's and an F in that formula, doesn't mean they're connected together, okay? So, polar, dipole-dipole. I don't know what's left. CO2 maybe? You know, we've drawn this one before. AX2, linear, non-polar, London. Okay? Is what you want to have for that one. Eventually, what we're going to do is I'm going to give you some compounds, and you're going to compare them. So you're going to kind of slot them in to where you think which one's the strongest, which one's the weakest, right? We got a little bit more notes to do for that, and we will do that probably tomorrow. But that's eventually what we want to do with that. All right? Any questions?